Okay, so welcome. We are now doing dynamical systems, fixed points, and other cool stuff like that. So, in the last lecture that we did, we were looking at calculus and how calculus can be used in economics. Now, what we're going to be doing is we're going to be talking about dynamics and how dynamics can be, well, similarly used in economics, namely in macroeconomic modeling. So, let's go ahead and get started. Well, first thing you're probably going to be wondering is what are dynamics? Well, dynamics encompasses the mathematical models with time that link different time periods together. It's particularly useful in macroeconomics because, well, we deal with time series a lot. We're going to be getting into some time series soon, but time series is really just a fancy way of saying that we're looking at statistical observations over time. So let's say the data we're analyzing for an empirical understanding of the macroeconomy is recorded over time, where the ordering of this matters. Then we're probably going to want to use theoretical models that also make use of these assumptions regarding time. This is ultimately so that we can try to link some of these theoretical models to the empirical models. So let's talk about time. What time is it? Well, it's peanut butter jelly time with a baseball bat. Anyways, moving along. So macroeconomics has time series analysis. We need to know basically what this stuff looks like in a more concrete sense. Namely, what does it look like mathematically? Because I can sit here and give you this really nice abstraction all day, but it's not really going to mean very much. So with some sort of time series stuff, we're going to have one observation per time period. So we would have like a sequence of events. So we would have like x sub 0, x sub 1, x sub 2, x sub 3, so on and so forth. Now, the sequence, as I just showed it, shows every element of the sequence as independent of the others. Now, the ordering still matters. I don't want you to think that we can do like x0, x2, x4, x1, x3. The ordering still has to, well, be ordered the way that it has been recorded. But if we're looking at it like this, it's independent. It's saying today has no impact on tomorrow. So it's not really a dynamic setup, right? So these subscripts represent points in time. So what I could do is I could re-express this equation as, well, x sub t, xt plus 1, xt plus 2, x sub t plus 3, so on and so forth, like that. And this would be referred to as static because, well, these are independent observations. The ordering does matter, but the observation, say xt plus 1, is not a function of xt. It's just a function of xt plus 1. So even though there are different points in time being looked at, none of these observations have anything to do with any of the other points in time. There's nothing linking them to a different point. So these are repeated, totally independent realizations of some variable. Now, when we're looking at time series, the actual data that we're looking at will be recorded as you just saw. So it'll technically be like static analysis that we're looking at. But these are, technically speaking, dependent on each other. And so we want dynamic stuff. How do we make it dynamic? Well, to be dynamic, there has to be some sort of a link between today and either yesterday or tomorrow or really any other point in time. There needs to be some kind of an intertemporal link between two or more periods. Now, a dynamical system is a function, or really a system of functions, that maps a set x into itself. So if we have some function f, we would say that f is a function where x is mapped back into x. So if we take an element of x, call it, say, x sub I, mathematically we would say this xi is contained in x, or xi is an element of x. We would put it into the dynamical system. We would get another element of x as the output. We'd call it x sub j. Now, x sub I may or may not be equal to x sub j. We'll get into cases where they are, in fact, equal to each other, and that's a particularly interesting case that is really behind everything that we're doing in this lecture. The sequence given in the previous slides can be dynamical if each element of the sequence is defined as a function of previous iterations of itself. This would mean that today's value is a function of yesterday's value, or yesterday's value and previous values as well. It's kind of like saying past behavior helps predict future behavior. So let's say that we have some sequence of events that can be related to another time period. So instead of what you saw in equation 1, we can add something to it and augment each. It says y sub t here. It's really supposed to be x sub t. My mistake on that. We can augment each x sub t term, where xt is equal to alpha 0 plus alpha 1 times xt minus 1. The next period, xt plus 1, would be xt plus 1 equals alpha 0 plus alpha 1 times xt. And the next period after that would be xt plus 2 equals alpha 0 plus alpha 1 times xt plus 1. So what we can see is, as we're updating these time subscripts, the left-hand side of the equation is always at, say, time t, where the left-hand or the right-hand side of the equation would be at t minus 1. If the left-hand side is xt plus 1, then the right-hand side is going to be xt. So the right-hand side is always one time period before what you see on the left-hand side of the equation. We also want to note here that the alpha 0 and the alpha 1 terms are time invariant. They're constant. And that's something that is going to be of particular use to us. It's of particular interest to us in the sense that we want this stuff to be time invariant. Or at least we want the alpha 0 and alpha 1 parameters to be time invariant. Now, this equation has a linking term between xt and xt minus 1, or xt plus 1 and xt plus 2 and xt plus 1. The dynamic relationship doesn't just have to be one period. We could have it for 2 periods, and we could also have it for 3 periods if we want. However, if we are, while we can have 2 periods or 3 periods, something like that, it's not really something that we're going to be looking at in the context of this class. Some more advanced macroeconomic models will use multiple lags, but in what we're going to be learning in this course, it's really just going to be if you're looking at one lag. Now, let's look at a mathematical example that I totally came up with on my own. Let's consider the following equation. So we've got xt plus 1 equals 3 plus 1/2 times xt. Well, if you see a subscript t, that implies that we're in discrete time. If you see something like x of t, it implies continuous time. Not everybody obeys this convention, but we're going to because, well, that's just kind of the right thing to do. We'll be dealing only with discrete time in this case. Continuous time gets a little weird. It adds a lot of calculus. I don't want to mess with it. And not to mention, most business cycle models tend to use discrete time because, well, the observations are pretty far apart. So, if we're looking at a monetary model, we would see something along the lines of data that's like monthly or quarterly data, something along that timeline for the frequency. So if something's separated by a month or 3 months, you're probably not going to want to use continuous time, because continuous time would be implying that all the observations are really, really, really close together. And here, well, they're kind of spread out. Anyways, the variable x at time t plus 1 is described by how it was behaving at time t. This is called a recursive relationship. If we can relate the state at one point to the state at another point in time, expressing it in terms of itself, it's a recursive relationship. And it tells me how all this behaves, but I need some kind of a starting value. This is what's referred to as an initial condition. So let's say the initial condition is x naught equals 10. Well, we can iterate this forward a bunch, and you can kind of see what's going on here. So what I do is I'll have xt plus 1 equals 3 plus 1/2 times the initial condition. So the initial condition, which at xt, or we'll say at x naught, where x naught would represent the starting point. So this is kind of where everything begins. The world begins at x naught, and the initial input of that is 10. So we would get 3 plus 1/2 times 10, right? 3 plus 1/2 times 10 is 3 plus 5. 3 plus 5 is 8. Well, since xt plus 1 is equal to 8, I can take that and plug it in for xt plus 1 in the function that has xt plus 2 equals 3 plus 1/2 times xt plus 1. So if I were to plug that in, I would get 3 plus 1/2 times 8. Well, 1/2 times 8 is 4, so 3 plus 4 is equal to 7. And from that, I can take xt plus 2 equals 7 and plug it into xt plus 3 equals 3 plus 1/2 xt plus 2, which gives me xt plus 3 equals 3 plus 1/2 times 7, which is 6.5. If I iterate it forward once more, well, I would get xt plus 4 equals 3 plus 1/2 times 6.5 is equal to 6.25. And if we keep plugging these previous values in, so the output of, say, xt plus 1 equals 3 plus 1/2 xt, that output becomes the input in xt plus 2 equals 3 plus 1/2 times xt plus 1. So the output from the previous iteration becomes the input for the next iteration. And if we do this, what we're going to see is that these outputs are getting smaller and smaller, but they're doing so by smaller amounts. So by recursion, or taking these values of the output, plugging them back into the function, we start approaching a number. Another way to say this is we are seeing that the system is converging to some number. And as we let this go on and on and on, we'll see that it would start to converge to the number 6. Now, when I said that a dynamical system is a system, really, or in our case, just a function that maps a set into itself, where f was a function that mapped x into x, for a fixed point to exist, which is the thing that we're really going to be interested in this chapter, there has to be at least one point where f of x is equal to x. This goes back to what I said about the inputs xi generating output xj, where xi may or may not be equal to xj. In this case, xi is equal to xj. When that happens, we get a fixed point. It's a point where the function of x equals x. So as we see, if we go back a little bit, here, xt plus 1 equals 3 plus 1/2 times, and what we would actually see is like xt, right? If xt plus 1 and xt are equal, or actually if we look at equation 10, we'll see xt plus 2 equals 3 plus 1/2 xt plus 1. Well, what would happen is xt plus 2 and xt plus 1 would be the same. Is there some input x, is there some input x where xt plus 1 and xt plus 2 are equal to each other, where the input equals the output? Let's see. So when we get a fixed point, that's where the input is equal to the output. And it's a point where the function of x equals x. So an element of the function's domain is mapped to itself by the function, giving us an element from the range that is equal to an element from the domain. So let's think about the general form that we need to get a nice little algorithm to solve out this type of a model. So if I'm going to generalize things a little bit, what I would get is, say, xt plus 1 equals a plus b times xt. Initially, I had the alpha naught and alpha 1, but a and b just seem easier, so let's just kind of stick with that. So if I've got xt plus 1 equals a plus b xt, where x sub 0 equals c, I would say xt plus 1 is a dependent variable. It's dependent upon xt, or the input from the previous period. The initial condition c equals x naught, and the values a and b, which are called parameters. Now we can use this information to get a nice general form for the solution. So from this function here, I can find the steady state or fixed point. So mathematically, it's a fixed point. In economics, it's sometimes referred to as a steady state, by setting every single xt plus 1, etc., just equal to x star, x sub ss for steady state, something along those lines, right? But what I want is for the input variable to be equal to the output variable. So I'll just get x star equals a plus bx star. Now from this, all we want to do is just solve for x star. So I'm going to subtract bx star from both sides. So I get x star minus bx star equals a. I'm actually going to stop saying the star thing and just say x minus bx equals a. I think we all pretty much know what's going on. So I'll factor out this x from x minus bx, which gives me x times 1 minus b. And x times 1 minus b is going to be equal to a. So I'll divide both sides by 1 minus b, and I get x equals a over 1 minus b, which is the general solution for x for this particular dynamical system. So if you ever see anything like this, or if you see xt plus 2 equals a plus b times xt plus 1, xt plus n equals a plus b times xt plus n minus 1, etc., all you do is just set the x's equal to each other and then solve for x. So the solution is always, always, always going to be a over 1 minus b. But there's a couple of caveats to this. The first, well, b has to be in this interval of 0 to 1, where we can include 0, but we can't include 1. So b can be anything from 0 up to, but not including 1. B can be 0 if we want it to be. It wouldn't be a particularly interesting system because we would just have a totally flat line, but, it's something that we could have if we wanted. B can't be equal to 1 because if it is, then you have to divide by 0, and that doesn't really work out very well. So if we denote x as the fixed point to this equation, then f of x equals x. So in this case, where x was equal to 3 plus 1/2 times x, well, x equals 3 plus 1/2 x. Solve for x, we get 1/2 x equals 3. X equals 6. Now, what it looks like is this right here. So you see that there are two lines. There's a 45-degree line where xt plus 1 equals xt. And then we've got our actual function that we're interested in, xt plus 1 equals 3 plus 1/2 xt. So what happens, what we're interested in, is if we've got this 45-degree line, so this 45-degree line that I'm dragging the mouse across is where x equals x. So the input exactly equals the output. Wherever you are, the input will be equal to the output. So along this line, xt equals 8, xt plus 1 would also be equal to 8. Xt equals 3, xt plus 1 is equal to 3. Where this function, the function that we're analyzing, where it is crossing, where it intersects with the line xt plus 1 equals xt, is the fixed point. So if the slope is less than 1, then we will get a fixed point. So let's think about what is going on here. So we started at x equals 10, right? So this was our initial condition, xt equals 10. Well, at xt equals 10, this is where we get 8. So we're going to have xt plus 1 equals 8, right? Because if we just draw this line all the way over to the vertical axis, we would get xt plus 1 equals 8, right? But the input was 10, the output was 8. So that's not a fixed point. This isn't a fixed point here. So when we draw this over, right, what we're going to want to do is just draw this line down, right? Because this is xt plus 1 equals 8. We draw it down to xt equals 8. So boom. We evaluate it. We evaluate xt plus 1 when xt is equal to 8. What does that give us? Well, that gives us 7. So this is where xt is equal to 7. So here we plug in 7 for xt. We evaluate what the next xt is going to be, which gives me 6.5. Evaluate it again, 6.25. And what happens is we staircase our way down over to the fixed point. So if we were to zoom this little picture in here, you would see more staircasing. Zoom it in some more staircasing. Zoom it in some more staircasing. But what we do is we end up converging to x equals 6. So we'll never actually touch x equals 6, but we'll get really, really, really close. And the further we evaluate it, the closer and closer we get to x equals 6. If we started at xt equals 3, well, it would be the exact same thing. It's just we would staircase upwards instead of downwards. So whether you start above the steady state or below the steady state, you converge to the steady state so long as the slope is positive and less than 1. So it's, like I said, in economics, it's sometimes called a steady state when the fixed point is what's known as an attractor. Here, this fixed point, x equals 6, is an attractor because no matter where you start, you will be drawn, it will be attracted to x star equals 6. This is an attraction because, well, the system is tending towards that point. Now, not that kind of attraction, although it is a really fantastic movie. I'd highly suggest you watch it. Casablanca, one of the greatest films, if not the greatest film ever made, period, ever. And that, great. So let's try to change these parameters A and B a little bit. Let's see what happens if we really just play with B. We're going to sort of leave A where it is. But let's say, we just keep A at 2. B is now negative 1/2. What happens? Well, we initially had 2 plus 1/2 xt. Now it's 2 minus 1/2 xt. So as I try to solve this out, I'm going to get x equals 2 over 1 minus negative 1/2. Well, that gives me 2 over 1 plus 1/2. So from 2 over 1 plus 1/2, I would get 2 over 3 over 2, which gives me 4 over 3. Now, when the slope is negative, so when b is negative, but it's still between -1 and 0, excuse me again, that burp was brought to you by Mountain Dew. Thanks, Mountain Dew. Anyways, we oscillate to the fixed point when the slope of b is negative. Now, without an additional example, I'll just tell you if b is between -1 and 0, then you oscillate to that fixed point, which leads to a couple more conclusions I'm just going to explain to you. I'm not going to show you because it's really just not that important in our context. If we change b around, what we'll get would be the following ranges that would give us certain types of fixed points. So if b is positive but less than 1, the system converges to its fixed point with no oscillation. If b is greater than or equal to 1, there is no fixed point. If b is equal to 1, what happens is that xt equals xt plus 1, that 45-degree line, is exactly parallel to b. Or not b, sorry. That line is parallel to whatever the function is that we're looking at. If they're parallel, well, those two lines will never cross, so there's no fixed point. If it's larger than that, well, they'll, again, never cross each other in positive input space, right? Because there would be like the negative space where they would cross each other, but we're looking at positive values of time. What the hell's a negative value of time, right? It's all positive stuff. So when we're looking at it that way, there's no fixed point. So if we were to evaluate a function where b is larger than 1, we'll diverge further and further with additional iterations of xt, and there's no fixed point. So if there was a system with b, say, larger than 1, every single time you took the input of the previous iteration, it would be a bigger and bigger number. It wouldn't be getting smaller. So that means if the slope b is larger than 1, it doesn't intersect with that 45-degree line. As opposed to when b was less than 1 but positive, or really just non-negative, when it got smaller and smaller, it would eventually converge to a fixed point. Now, if b is negative, there's a fixed point, but you oscillate in getting there. So where you saw that staircasing in the case where b was between 0 and 1, you'd see that staircasing. What happens with the oscillation is it would bounce from one end of that fixed point to the other end, and it would keep bouncing back and forth and eventually oscillate in approaching the fixed point. So if you started where the point was above the fixed point, the next thing you would iterate to would be where it's less than the fixed point. When you iterate that, it's larger than the fixed point, then less. Larger, less, larger, less. But every single time it gets a little bit closer to that fixed point, and eventually it converges to it. If b is -1, the system oscillates between two values, but it doesn't ever move away or toward any fixed point. Why? Well, because technically speaking, it's parallel. If b is less than -1, the system oscillates, but every iteration diverges further and further away from the fixed point. So yeah, oh my God, I just realized I hammered you guys with a ton of math. I promise you, I'm not a mathematician trying to masquerade as an economist, trying to just give you tons of math or anything like that. I'm not trying to do that. So here's the deal. We're going to go ahead and call it quits for this lecture. You can enjoy this lecture. There will be another lecture coming up where we actually start talking about a little bit of economics. We're going to be looking at, so I'm skipping the time series lecture for just right now. Instead, we're going to look at a little bit of stuff regarding some monetary economics and sort of the role that money plays with like different relationships with other economic variables. And from there, we'll get into some general equilibrium modeling. So until then, have a great day. There should be another lecture posted up in the next day or so. And yeah, enjoy things. So thanks.